Welcome to this brief presentation of my HealthMap terrain application. You can display the help menu pressing the H key, and you will have the list of the available commands and the associated key there, and you can press H key once again to hide this menu. You have in the bottom a banner with informations. You have the quality or smoothness mode here, distortion or tessellation factor there. You have the duration of single frame in millisecond. You have the number of patches of the model, the number of patches sent to the pipeline, the number of triangle reaching the fragment shader, and also the number of triangle discarded by the pipeline. We start here with a single terrain instance based on the small HealthMap, 128 by 64 pixel maps texture, and we can represent that map here with two sets of points. The green one points on the ground, and the red one points integrating the altitude. And we can have a wireframe representation of that same map as a net, and you can see actually that the surface representation is a little bit different from actually the map. You can see difference here, for instance, there, and we remove that representation here. Let's see now the wireframe representation associated to the surface. You see actually all the different patches were limited by the green edges, and the inner triangle limited by the blue edges. As you can notice, most of the patches in this configuration have a minimum tessellation level. The patches like this one is made of only two different triangles connecting actually the four corners, and this is the tessellation except for some transition zone there, here, where actually the slope is the less constant, and you have especially here actually more inner triangles, more than two. We have a second wireframe representation for the normals. The white normals are associated to the triangles, and the pink normal are associated to the map itself. It's computed for the map, and we can actually combine both representations. You are able to increase or decrease the distortion or tessellation factor. Here we increase actually that factor. It means that for many patches the number of tessellated triangle is higher, except in very constant zone, slope zone like this one apparently. And of course it depends on the distance to the viewpoint actually. It means you increase a lot the tessellation in the front, but not actually in the rear part, far away from the observer. It's important to notice that we are here in a non-uniform actually situation. Two adjacent actually patches may have different tessellation level. This one is higher than this one, but if you consider the common edge between those two adjacent patches, the subdivision is the same. We have here three subdivisions, three different segments, and two inserted point there, and you can see it's the case for this patch and the adjacent one, which mean actually the different triangles here connecting to that edge are connecting together. Then you avoid any cracks in the representation model. Let's consider now the quality or smoothness level of representation. The default mode is linear ace interpolation and constant normal, which means actually that the normal is constant over a zone. Let's see here, for instance, here, if we change a little bit the distortion factor, it's more obvious. Here you have some constant normal zone, then you have some visual artifacts that's not satisfactory at all, and you have discontinuities in normals, then in lighting, then in representation. We can change the mode and to switch to a linear interpolation for both ice and normal, and you see you get smoother results, and you don't have that visual artifacts anymore. And we have finally that bicubic interpolation mode for both ice and normal, which used actually a degree 3 polynomial surface to interpolate actually the sample of points of the map. Let's consider now 4 different animations. We have the first one, the fly animation, which allows us to see the adaptative process of tessellation. It's more obvious once again if you add the wireframe representation, and you can see the tessellation level increase as far as the patch is coming in the front zone. You can of course decrease and increase the representation, the tessellation level, during that animation. The second animation is the simulation of the sunlight from rise to set, which simply modifies the position of the sunlight, the lighting position, and a little bit the color from white to orange actually. We have a third animation, which is a building simulation of the terrain from the ground to the top. We can also add the wireframe representation, and we'll figure out that from the beginning, where it's completely flat, the tessellation is minimal and is getting higher. We have the opposite animation from top to bottom. Perfect. And then we have a coloring function using 8th color map. And we have also an isoline function drawing lines of constant altitude with different steps. And of course, here we have a very high distortion factor, quite high. Then the resolution of the isoline is good, but if we decrease it, it's getting worse and worse, and back to the high level of tessellation. And eventually we have a shadow function implementing a shadowing process as an alternate method to shadow mapping. Oops. You can see here, which is actually not satisfactory because of performance issue and also quality, especially regarding the age of the shadows here. Let's use the sunlight animation to see. Oops. Once again, maybe slower here. And that's all for this presentation. I remind you that you have a free access to the complete code on GitHub, and I thank you very much for watching. Bye bye.